Welcome back, engineering students, to this explainer on humanoid robotics. So, did you know that a single misstep in a physical prototype can literally destroy a $50,000 actuator in a fraction of a second? Yeah, it's brutal. As your technical mentor today, I'm absolutely thrilled to walk you through exactly how we avoid that nightmare scenario. We're diving into one of the most absolutely crucial phases of robotic development, and that's stability analysis. Look, designing humanoid robots that can actually simulate human movement, balance, and dexterity, it's an immense challenge. But today, we're going to analyze that stability, and the best part is we're going to do it without breaking a single piece of expensive hardware. Okay, let's dive right into this.
Think about it like this. Before a robot ever takes its very first physical step, it has to learn how to stand in a virtual world. Why? Well, because physical engineering is incredibly expensive, and early-stage prototypes are notoriously fragile. A single fall, just one, can destroy months of hard work and thousands of dollars in specialized components. And that is exactly why virtual simulation, specifically using environments like Blender, is the risk-free foundation of modern engineering. It gives us this incredibly robust physics-based sandbox where we can test, tweak, and refine our designs long before we ever commit to actual physical production.
All right, here's our game plan for today's masterclass. We'll cover virtual prototyping value, the CAUTO spine architecture, kinematics, stable scenarios, and finally, we'll test some unstable environments.
Okay, kicking things off with Section 1, the value of virtual prototyping, building the foundation.
So, before we can test anything at all, we've got to actually build our environment. Developing a 3D humanoid robot model requires a pretty meticulous 4-stage process. First up, we have mesh construction, where we basically use primitive shapes to build the physical body parts. Next is the armature setup, and this acts as the robot's skeleton for animation and movement. Third, and this is absolutely crucial for our testing, is applying rigid body physics to simulate actual, real-world physical behavior. And fourth, we set our frame rate and time steps. For our setup, we're establishing a super smooth 60 frames per second to ensure high precision. It's a brilliant workflow that really illustrates how a digital twin is systematically constructed from the ground up.
Moving right along to Section 2, the CAUTO spine architecture, bioinspired balance. Now, for our analysis today, we're looking at a very specific, incredibly lightweight 3D printed humanoid model. It stands 850 millimeters tall and weighs just 3.6 kilograms. But its absolute secret weapon for balance is the torso mechanism known as CAUTO. CAUTO stands for CASINO Humanoid Torso. It's a highly bioinspired mechanism that actually reproduces functional spine units. It's literally mimicking human biology to maintain balance. And this isn't just to look cool. This spine gives the whole system an additional 3 active degrees of freedom. It acts as the absolute core for walking balance, complex navigation, and intricate manipulation tasks.
Let's look at the hard numbers here, because honestly, the engineering data is incredible. Check out the specifications for this CAUTO mechanism. It has a mass of just 1.2 kilograms, but it provides a massive 4 degrees of freedom. We're talking bending angles, direction, axial torsion, and axial elongation. And the crazy part, it achieves all of this through a tendon-driven architecture using just 4 servo motors. That means those 4 tiny motors are actively controlling those crucial degrees of freedom, constantly keeping the entire upper body dynamically stable. It's really elegant engineering.
Which brings us nicely to Section 3, forward versus reverse kinematics, the logic of movement.
Now, as engineering students, you've absolutely got to wrap your heads around kinematics, basically how forces propagate through the robot's joints. We rely on 2 primary principles here. First, forward kinematics, or FK. This is where you rotate parent joints to propagate movement down the hierarchy. Think of it like moving your shoulder, which then forces the elbow to move, which then moves the hand. We use FK heavily in early pose setups. But then we have reverse kinematics, or IK. This is the game changer. This is where we manipulate the end effectors, like the hands or the feet, and the system automatically calculates the necessary joint angles for the rest of the limb. Think of IK like catching a heavy medicine ball. Your hands meet the target, and your nervous system instantly calculates how your arms, your shoulders, and your core must bend to absorb that weight. So the main takeaway here is that IK is absolutely critical for maintaining balance. It allows the robot to plant its foot firmly on the floor and then naturally adjust its hip and spine to adapt to that fixed placement.
All right, Section 4, running stable simulations, proving the concept.
Let's actually put this into practice and analyze our Blender simulations. To establish a baseline of perfect stability while we adjust the robot's posture, we use very specific mathematical parameters. We enable pose mode on the armature to adjust the stance. Then we set our physics substeps to 20 and our solver iterations to 20. Running that at 60 frames per second over 300 frames gives us exactly 5 seconds of highly accurate, rock-solid simulation. These high iteration parameters, that is our mathematical safety net. It's what keeps our virtual robot firmly planted while it shifts its weight around.
But hey, internal posture isn't the whole story, right? We also have to account for the ground right beneath the robot. By optimizing the material properties in our simulation, we create high-friction surfaces beneath the robot's feet. This material optimization is what directly prevents the robot from slipping during those intricate pose adjustments, because let's be real, a mathematically perfect pose means absolutely nothing if your virtual floor is made of ice.
Finally, let's jump to Section 5, Testing Unstable Environments, Pushing the Limits.
You know, a good engineer doesn't just prove a design works. They figure out exactly how to break it. Let's deliberately provoke instability here by tilting the virtual ground. We're going to rotate the ground -9 degrees on the x-axis, -6 on the y, and -7 on the z. Furthermore, let's purposely reduce our simulation precision. We'll drop the substeps down to 10 and the solver iterations to 15. And the result? Well, the robot completely loses its balance and topples over. This brilliantly illustrates just how uneven terrain, when combined with a lower calculation fidelity, can drastically compromise a bipedal stance.
Next up, we introduce some direct physical interference. We're going to place a simple, hard, rigid body cube directly under the robot's left foot. Even if we have a perfectly stable posture configuration, this slight, unexpected elevation difference on just one foot entirely disrupts the center of gravity. The second it makes contact with that cube, the robot's balance is broken, causing a complete and total fall. It really goes to show just how incredibly sensitive humanoid balance is to real-world obstacles and improper posture adjustments.
So, what is the big takeaway from this explainer today? As your mentor, the core lesson I want you to internalize is that running these highly specific virtual simulations in platforms like Blender completely empowers us as engineers. We can test different friction materials, complex kinematics, bioinspired spines, and hazardous tilted terrains, all right from our workstations. We can refine our control strategies and validate our mechanical structures meticulously, completely bypassing the immense costs and physical risks of traditional hardware development. Virtual testing isn't just some neat shortcut, it's a vital, cost-effective requirement for doing modern robotics right. Which leaves us looking squarely at the frontier of what comes next. We've proven foundational stability in a highly controlled virtual environment. But the real world is messy and dynamic. So think about this. With these virtual models perfected, how will integrating real-time sensor data and machine learning algorithms for instant, on-the-fly posture correction redefine the future of terrain-adaptive robotics? The foundation is built right here in the simulation. The next step is teaching it to truly think on its feet. Thank you for joining this explanator, students. Keep innovating, and I'll see you in the next analysis.